Okay, very good. So let me expand this. Today is a continuation of our previous meeting. And last time I talked about the Taylor expansion of a function from Rn to R. And we looked how, we saw how the Hessian and the gradient appear at the expansion of order 2, and how positive definite metrics, how that is related to minimum and a minimum of a function. So if the Hessian is a positive definite matrix in a neighborhood of a point, then and the first necessary condition that the gradient is 0 is met, then we see that it's a local minimum. Now, if the Hessian is positive definite for the entire domain, then the function is convex. Basically, we'll be going back to this Taylor expansion, and we'll use it in various ways. And one point is that the Taylor expansion has, if you just expand to the second degree, then it's a quadratic form. So it's interesting to closely understand the behavior of quadratic form. So that's the purpose of today's meeting. Now, just maybe before I go into that, maybe just a quick step backwards. I want to, this is a study group on machine learning. So I want to give you like a concept map of what we are doing, which may be helpful because we haven't done this for a while. So let me draw here a concept map quickly of what we're doing. So when you think about machine learning, this is machine learning. Okay, machine learning. There's basically two sources that of mathematical assets that you need to think about. One is optimization. And optimization is a very wide area in mathematics. It draws upon calculus and measure theory analysis, as well as convexity and algebra. So optimization is one area, or to be more precise, numerical optimization. And the other source is probability and statistics, which are kind of related. And they draw upon concepts that have to do with probability, have to do with statistical tests, have to do with decision theory, has to do with utility theory, game theory. All of that comes into this. And now, when you get to machine learning, there's two aspects of a machine learning problem. One is the search, okay? And the other, so you have to formulate the problem. So you use some loss function for formulate the problem, which result in an optimization problem. So formulating the loss function result in an optimization problem. Then you have a search problem. When you get to the search problem, you basically you've reduced the problem to optimization. But then on the other hand, you have the generalization problem that makes it interesting, which basically means that here in our context in machine learning, the search, the solution of the optimization problem using a search algorithm like gradient descent is a mean to an end. But the actual thing that you want to do is get the right generalization, which means that the model that you get is going to work well in operation once it's deployed in the real world, so to speak, once it's being used. So that I hope that concept map is very helpful. The loss function embodies in it things from utility, decision theory, game theory. All of that comes into the definition of what you're trying to solve in terms of an optimization problem. So that's a quick, concept map of what we're doing here. And so we jump around. So sometimes we are here, sometimes we are here, sometimes we are here, sometimes we are here. And, maybe it's useful for me to tell you that where we are in this concept map. So just to place today's discussion, we are in the optimization portion. Any questions or thoughts about this? Okay.
So Eitan, you're just optimizing the loss function right now. You're not addressing generalization with what you're discussing today?
Yes. So today we don't talk about generalization. We can just forget about generalization. Think about the optimization. Now, this is actually a very interesting point, because sometimes when I do like mentoring of machine learning, it's something that people don't understand. So they say, okay, I've solved the optimization problem, but it's only a mean to an end. That causes a lot of confusion. So that's the concept map. It's a very important concept map to understand. So today we are talking optimization. Now within optimization, because a lot of optimization is based on Taylor expansion, we are in Taylor expansion to the second degree as a quadratic form. We will gain benefit by understanding the quadratic form more closely. So this is what I'm going to do today, and it will have some very funny consequence that you can use in practice, which I'll mention. But let me start what a quadratic form is. So this is a quadratic form. So Q is a matrix. This is a function from Rn to R. Q is a matrix, B is a vector. Let's see what the dimensions of everything here is. So X, this is a function, the quadratic form is a function from Rn to R. So X is a vector. And then Q, because I'm multiplying the matrix on the two sides by X that has a dimension n, this matrix should have a dimension n times n. And the vector here, this is the scalar multiplication. So the vector here should also have a dimension n. And C is a scalar. And adding all these three scalars, you get the value of the function. So this is the quadratic form. If you choose n equals 1, you just get the familiar equation that we've learned in high school, right? Here Q and B are scalar. Any questions up to now? Okay. So by analogy, so first let's remember what we've learned in high school. So the derivative of f is going to be this, right? Because it's 2 times qx over 2, which is qx. And this is the derivative of this is minus b. The derivative of a constant is 0. So this is the derivative. Okay? Now the necessary condition for a minimum or maximum, sometimes called the critical condition, is going to be that the derivative is 0. And that gives us that qx should be equal to b. And the second derivative is q, because b is a constant and qx, the derivative of qx is q. And then if q is bigger than 0, then it's a minimum at qx equals b. So I hope this is not new to anyone. This is something I usually learn in high school when we learn calculus and we learn how to solve maximum and minimum problem with one variable. Any questions or comments on that? Everyone familiar with what I've shown up to now? Yes, no?
Yeah, so far it makes sense.
Yes, okay, great. Okay.
Yeah, even I remember that from high school.
Great. So now let's take it a step forward, and we'll use analogy. So by way of analogy, the scalar multiplication here of bt times x, where b is a vector and x is a vector, is going to be, if you take the derivative here, it's going to be just b. Okay? I mean, try it out. Like, take this and you know, think about the partial the partial derivative of by each of the n variables, and you can quickly see that this is correct, and you get B. But by analogy, you would expect it to be, because this is a linear function. So it's like minus bx here with one dimension. So you would, by an analogy, you would expect it to be b, and it's easy to check that it's actually minus b. Okay, the way you expect it. In a similar way, think about this, like x transpose qx as q times x to the square of 2 in one dimension. And then by analogy, you get again that the derivative of this is qx. And if you expand the matrix operation and actually calculate the partial derivatives, you'll get qx. You can verify it. But you don't have to if you just use the analogy. So this is the gradient, and again, for a point to be either a local minimum or a local maximum, you need to equate the gradient to 0, and you get the same, well, not the same, but by analogy, the same condition as you had before for the one dimension. Basically, you get that qx equals b. And this is very different than the one we had in one dimension, because q is a matrix and v is a vector. But it looks very similar, right? And the analogy works. So what you need, it turns out that what you need to do in order to find the critical points of the quadratic form, the point that are either minimum or maximum or something else, but they are the points that you need to consider, is to solve a linear equation. Specifically that qx equals b, find the solution of this linear equation. Now, because we assume that q is positive definite, q has an inverse, so we can solve it. In principle, we can solve it by finding the inverse of q, or by using a Gaussian method of elimination. So, any question or thought about that? Marcel, did you try to say something?
No.
Okay. 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 So the next analogy is the second derivative, which in our case, by analogy again, it's just q. And again, if you take qx minus b and you calculate the Hessian, this is the Hessian. Take all the partial derivatives and for partial derivative j, you then do the partial derivatives x equals 1 to n, and you get a matrix. So that matrix will happen to be, in our case, will happen to be just q, the quadratic form. As I said, we assume that Q is, we assume that Q is positive. So here we assume that for any X, this is bigger than 0. That's the definition of positive definite, which is the analog for Q bigger than 0. That means that F is convex, and that means that Qx equals B is a minimum, actually the global minimum. Yes? So you see a very straightforward analogy between what you're familiar with from high school and the way you handle a quadratic form. In every step here, you just need to do some calculations. If you're familiar with matrix calculation, you can quickly establish that the analogy works. Just a simple exercise. So any questions or comments up to now?
No, I think I followed. Thank you.
Great. So one of the most basic techniques that we use in machine learning, and then there's other variations that overcome different issues, is the gradient descent, or sometimes people call it the steepest descent. So basically, we talked about it previously. The idea is that the gradient is the direction in space in which the function is increasing most rapidly locally at a point, and minus the gradient happens to be the direction in space in which the function decreases most rapidly. And basically what we're saying here is that we're going to take a step in the direction in which the function decreases most rapidly, and the length of the step C is something to be determined, and there's actually a lot of thought given to how to determine it exactly. But that's this line basically is the standard gradient descent. Now that we know what the gradient is, we can substitute the gradient here, and we get the gradient descent for quadratic form. So this is basically, it's going to be a way to get to the minimum of the quadratic form iteratively. Okay? Question? Now,
None
yeah?
for me. Okay.
Now the interesting thing about this is that so the critical point here is actually the solution of this linear equation. Now, if Q is very big, which is what we get with machine learning, then solving this linear equation is going to be very hard. Okay? Because like applying Gaussian elimination will be inefficient because Q is maybe very, very, it may be sparse, but it has a huge dimension, and as you start the Gaussian elimination, it will stop being sparse, the intermediate matrix, and then you would not be able to apply Gaussian elimination to solve this linear system. So one of the funny things about the quadratic form is that one of the ways to solve a sparse linear system, because it's the critical point of the quadratic form, because the gradient is equals to 0, is to go ahead and apply gradient descent or something similar on the quadratic form that is associated with the linear equation that you're trying to solve. So what I've shown you today is a way to approximate linear equations that are very hard to solve by introducing a gradient descent or other search process on the quadratic form that is associated with the linear equation that you started from. Okay? Does that make sense?
Yep, I can follow.
Great. So next time you want to solve a quadratic, a linear equation that is sparse and the Gaussian doesn't work, it explodes. Think about the quadratic equation. Okay. So understanding. So that's just a side benefit for this presentation, but basically I wanted you to see in details how you solve a quadratic form, how you find its minimum, and how the gradient descent basically looks like. Any questions or comments on this? And the reason I wanted to show this is because we'll use quadratic equation, the quadratic form a lot in optimization, because it's the second order. Basically, that's how the second order expansion of a Taylor, the second order Taylor expansion of a function looks like. So, any questions or thoughts? Okay. So, thank you very much for joining today, and we'll continue next time.
That sounds good. Thanks, Eitan.
Great, thank you.
Thanks, Eitan.
Thanks.
Bye.
Bye-bye.